So today's question is also on piston cylinder and we're having work input via electrical unit. So W is electrical work input, and this is the piston and cylinder device. Inside it air is considered. Now let's take the system to be inside air and including the wire of electric. Now initial condition is 120 kilopascal, 300 Kelvin. Initial volume is 0.023 meter cube, and electrical work input is 50 watt for 5 minutes. So now pressure remains constant, so due to the some change in property, so some change in state of the system, so both the 1 to 2 state remain constant. From state 1 to 2 pressure remain constant, that is 120 kilopascal. So it is a constant pressure process. Now ambient temperature 300 Kelvin, ambient pressure 100 kilopascal. Find exergy destroyed during process. So for the whole process, exergy destroyed is to be calculated. Let's see. Let's take piston plus wire, this system, as we have said, from energy balance. So the work input must be equal to the work output plus change in internal energy of the system. So work input is WE, which is electrical work, and WB is the boundary work. Boundary work, which is PDV. PDV is P into change in volume. So delta U is change in internal energy of the system. So WE is equal to PDV would be, since pressure is constant, so just P into V2 minus V1, that is change in volume, plus mass into specific at constant volume CV, T2 minus T1. Now PV, assuming idle gas, PV is equal to MRT. So mass from here can be calculated. P1 we know, V1 we know, R we know, T1 we know. Putting all the values, we get 0.042 kg mass. Now, so putting this mass in above equation and all the known values, which is V1, P1, WE in above equation. So WE is in watt, so we have to calculate it in joule or kilojoule. Yeah, kilojoule is correct, kilojoule. So 50 watt into time in seconds would be 5 into 60, that is 300 seconds, and divided by 100 will give the value in kilojoule. So 15 comes out from this. Now 120 is constant pressure into V2 minus V1, which is 0.03, plus mass into CV, T2 minus T1 given value. So rearranging all these equation and solving this, we get this equation: 120 V2 plus 0.03 T2 is equal to 27.6. So let's give it as a equation 1. Now assuming idle gas, so P2 V2 is equal to MRT2. Now P2 is constant 120 into V2 is equal to mass into R into T. So V2 is equal to 0.0001 T2, and we'll give it equation 2. So from equation 1 and equation 2, putting the value of V2 in equation 1, we get 120 into this 120, there was 120 V2, so 120 this one 0.001 T2 plus 0.03 T2 is equal to 27.6. Solving this equation we get value of T2, as the temperature is at final state is 657.14 Kelvin. So from equation 2, volume would be, putting putting this value here, we get 0.0657 meter cube. Now let's do the entropy balance of the system. So entropy balance of the system would be entropy in minus entropy out plus entropy generation is equal to change in entropy of the system. So entropy in and entropy out would be 0 because there is no mass flow rate in or any kind of heat input to the input or out of the system. So these both the terms are 0. So S generation would be m Cp ln T2 by T1. Here the pressure term is not there because the pressure is constant and it would come out to be 0. So ST1 minus S21 minus S1 S2 minus S1 is equal to m Cp ln T2 by T1. So S generation, putting all the values, Cp is 1.005, mass ln T2 by 300 will give S generation to be 0.033 kilojoule per kg Kelvin. So the equation for exergy destroyed is equal to T naught into S generation. T naught is the ambient temperature. So ambient temperature is how much? Let me see. So ambient temperature is 300 K. So putting the value 300 into this S generation, we get 9.9 exergy destroyed. Now this question can also be done by just doing exergy balance also. So let's do the exergy balance. So exergy in minus exergy out minus exergy destroyed is equal to change in exergy of the system. Now exergy in is only work input, the form electrical work, minus exergy out. Exergy out would be boundary work minus P naught V2 minus V1, which is surrounding work, to push the work required to push the surrounding. This whole term is useful, total useful work output. Okay, because boundary work, some of the work required to push the surrounding, so we have to subtract it. So boundary work minus P naught V2 minus V1, which gives the useful work. So work input minus useful work out minus exergy destroyed, and for a closed system x2 minus x1 exergy change will be m mass specific internal energy change u2 minus u1 plus p naught v2 minus v1 per unit mass, so by m, minus T naught S2 minus S1 by m per unit mass. So putting all these values, 120, we have calculated it before, and this is 100. Putting these values, so it is P V2 P P2 minus V1, so it would become P minus P naught, which is P 120 minus P naught 100 into V2 minus V1, V2 minus V1 minus exergy destroyed is equal to, putting this value, mass, this is U2 minus V1, V1 would be CV T2 minus T1, so CV is 0.718 T2 minus T1 plus 100 change in volume divided by mass minus 300, and this is S2 minus S1 we have calculated, comes out to be equal to S generation, so it would be 0.033 divided by mass. So solving this whole equation, so exergy destroyed comes out to be 9.9 kilojoule.